You want to know something weird that doesn't get enough slack? Being continuous. It seems simple and straightforward at first glance, but it can showcase some wacky dark things. Now, how I always imagined the notion of continuity is the ability to somewhat smoothly fingerboard around a function without anything stopping you. Simple, right? For example, this, or even this. I mean, this definition even works for even more wacky things like this, or this. So there we go. I've done it. I've solved the problem of continuity with this amazing definition. Or so I thought. Until I saw absolute monstrosities like 1 over x. Like, how the flip are you supposed to skate that thing? So I thought it was not continuous according to my definition. But to my dismay, I still found that it's still considered continuous. So how about this? I mean, I guess I could finger skate over that. A point does have 0 width after all. But does that mean that it's still continuous? No, I mean, obviously not. I mean, it's in the name. The thing doesn't continue, it has a very visible hole in it. So sadly, another definition other than awesome fingerboarding is needed. Well, one way we could go about this is attempting to test if a function is continuous at a single point, right? Since that should be easier than trying to figure it out for the whole function. Attacking problems where they appear the simplest seems like a good way to approach this. Let's call this point P and we'll try to see how to mathematically show it's continuous. So how would we know if a singular point on a function is continuous? Well, at least I know a basic thing, that the point has to exist in the first place. I mean, a bit existential, but it's true. Since if the point wasn't defined at the point, at that domain, we would just have another hole again. And you cannot tell me with a straight face that a huge hole in our function is continuous. Okay, so we have this part, but we have some other anomalies to account for. For instance, what about this weirdness, where we're just chilling and then bam, our point P goes rogue and breaks our function into pieces. I think our new definition should clearly not count this as being continuous. I mean, just look at it. So how do we put it into mathematical terms that would work for any function? Well, first we should clearly note what we want to showcase first. What we want to show is that if you get really close to point P, I mean you could even say infinitesimally close, that the value should be the same as the value of P itself. So basically, if you walk to P from both ends, the value of the function or graph should get closer and closer to P. Now it turns out, thankfully, there's a problem that does exactly this: limits. I literally just stated the loose definition of limit, so to formalize our definition a little bit more, we should really include them. So bam, here it is. It states that as any x gets closer and closer to P, but never at P, the values should approach the value of P itself. So this weird thing that we had would not satisfy this equation, and so we would therefore consider it not continuous. So we've done it. This definition seems untouchable, unstoppable, and what's over there? A jump discontinuity? What? Well, I guess we have other things to take care of because our current rules don't really quite work at this point, since the limit doesn't even exist for point P in this case. So we can't even evaluate it for our conditions to be valid. This is true since if we approach from the right or left side of P, we get different values, so the limit just doesn't exist. Fine. For our third requirement in our ever-expanding definition for continuity, we'll add that the limit has to exist at point P. There. Now with this, we're almost done. Now since this definition was only made for a single point, we should really expand it to be used for functions, since that's what we really want. We should define a function to be continuous if, for every point in its domain, it follows these properties. And voila! These simple rules will work. Obviously you could get even crazier, more concrete definitions, like your epsilon delta definition or some other funky stuff, but for most cases this definition is most likely good enough. Going back to some function I couldn't figure out before, like 1 over x, we find that it's still considered continuous because its domain doesn't include the singularity. So because of that, it's still defined everywhere and has a limit everywhere where the function is defined. Because of this, some weird functions can still be continuous according to current math convention like this. Since we have our jump included in our domain, the limit doesn't exist there, so with our definition it's not considered continuous. But if we have something like this, just changing the bounds a little bit of the domain, we just don't even consider that point to exist. So now wherever our function has a valid domain, it has a limit and it's defined. And so it's continuous according to our definition that we just made. Now what's so mysterious about this? Why did I describe continuity as being weird? Well, it's because of how weirdly it applies to real world things which are very much discrete and not continuous at all. Nothing in this world is continuous. Don't believe me? Beams of light are quantized into mini photon packets. There are atoms and quarks, and we theoretically can't go down smaller than Planck length. But ideas like continuity are essentials for models that want to accurately model our real, discrete physical world. For example, here's an equation called the one-dimensional heat equation. Basically, this equation says that at a specific point in a metal rod or something like that, the change in heat is proportional to the second derivative. So you get this property of a heat sort of diffusing from hot places and spreading out to the cold ones. It seems to work pretty well to model heat diffusion in real life cases, but it uses a wholly continuous process. These partial derivatives in the equation require continuity to even be derivatives. If not, the notation of a derivative loses its meaning. But the heat of a specific molecule is not continuous at all. It changes discretely with how many times the microscopic molecule bumps into other molecules, or how many times a photon hits it and therefore it gains energy, which is totally discrete and countable, be it an extremely large amount, but still countable. So somewhat magically, this equation is still used to model real life because of its accuracy of predicting what happens, even though the way it does it is not really true to reality. The magical use of continuity is that it approximates real life phenomenon with stunning accuracy, even though it does not exist in real life. If you would like to delve into this a little bit more, I found inspiration for this video in Steven Strogatz's book, Infinite Powers, where he briefly goes over this strange and somewhat paradoxical property in calculus and how it's used in calculus for real life scenarios.